We had some homework from last week, worksheet number 17. Got some answers up there right now, 1 to 4. Have a peek at which ones you need gone over. Don't worry about the solutions to them right now. We'll take a look at the solutions in a moment. 1 to 4 up on the board. We'll go 5 to 8 here, if we can scroll down there. And finally, 9 to 11. 9 to 11 are the ones that are on total internal reflection, which whether you need one of those gone over or not, we're going to go over at least one of those questions from 9 to 11. Any issues with any of the questions from 1 to 11? Number 8? Any others? 10 to 11? We'll take a look at both of them. We got some time this morning, so we'll take a look at both of them. But in the end, I think if you're able to get one of them, you're probably going to be able to get the other one, right? Essentially both the same question. 9 as well, right? Pretty much the same question, as long as we have the indices of refraction. Any others? 8, 10, 11? Going once or twice? All right, 8, 10, 11 it is. All right, number 8 it is here. And number 8 says, oh, this is a good question, actually. I remember this one. Good question. Determine the ratio of the speed of light in crown glass to the speed of light in quartz glass. You guys have the table in front of you right now for the index of refraction of these different types of glass. Can somebody tell me what the index of refraction from crown glass is? 1.52. And for quartz glass? 1.47. Okay. We want to find the ratio of the speed of light in these mediums, from crown glass to quartz glass. Anybody have an idea here? Anybody have an idea as to where to start? I see a word there that tells me where to start. A single word. Does anybody else see that word? The word ratio. Yeah. What do we do when we see the word ratio? Another single word. It means the same thing as the word ratio. It also means the same thing as the word compare. Compare, ratio. What's the word? Starts with a D. What is it? Divide. We want to divide. We want to find the ratio of the speed of light in crown glass to the speed of light in quartz glass. We got to divide. So let's call this medium 1. Let's call this medium 2. We don't really know if it's going from medium 1 to medium 2, from crown glass to quartz glass or not. We're just going to call it 1 and 2 so that we can find our ratio here. We want to find V1 over V2. Now, if we have the speed of light in crown glass and the speed of light in quartz glass, this becomes an easy question at this point. It's just simply a matter of dividing two numbers, but we don't. So, does anybody have any ideas from here what we might want to do? Should we find V1? Maybe. Should we find the speed of light in quartz glass and crown glass? How might we go about doing that? Any ideas for that? You had a number of questions at the beginning of this worksheet that essentially asked you the same thing. What's the speed of light in this medium? Emma, how could we find the speed of light in crown glass? Good. So in other words, you're going to go back to that definition of index of refraction, which is the speed of light divided by the speed in the medium. We're going to say N1 is equal to C, the speed of light in a vacuum, divided by V1. Okay, that's going to allow us to find V1. Okay, it's C over N1, which is 3 times 10 to the 8, and N1 would be 1.52. What does that give us for the speed of light in that medium? 1.97 times 10 to the 8 meters per second. All right, so let's put that in for V1 here. 1.97 times 10 to the 8 meters per second. V2, we're going to do the same thing for V2, right? But use the index of refraction of quartz glass. It's C over N2, which is 3 times 10 to the 8, divided by 1.47. It's going to give me a number that's slightly bigger, right? What does that give me? Somewhere around 2.0 something? 2.04 times 10 to the 8 meters per second. So let's plug this in here, 2.04 times 10 to the 8 meters per second. Now there's a little bit of a shortcut here. Anybody spot it? It's not much, but saves you a little bit of work on your calculator. You don't have to spot it. It's okay if you don't. You're still going to be able to do this question just as well as I can if you don't spot it then. If I get a 10 to the 8 on both the top and the bottom, why don't I just cross those off? Cancel. Right? So now I just divide 1.97 by 2.04. And what do we get for that? 0.98? 0.98? Yeah, okay. Yeah, that works actually. 0.98. So the ratio would be 0.98 to 1, right? Anybody do it differently? Because there is a different way to do it that can actually save you some time and effort. Quite a bit, actually. You can cut this question less than half. Listen, if you don't spot this thing that I'm about to tell you about, that's okay. This works. Okay? First thing that we spot there is the word ratio. We know ratio means compare. We know ratio and compare both mean divide. So divide V1 by V2. You don't have the values of V1 and V2. Generally, what do you want to do? Find the values of V1 and V2. Divide them, got the answer. Okay, we can do this question. We can all do this question in the way that I just showed you. But there is another way to do it as well, and I'm curious if anybody ever had this thought. V1 over V2. That reminds me a little bit of Snell's law. Sine theta 1 over sine theta 2, V1 over V2, lambda 1 over lambda 2, N2 over N1. Why can't we just do this? Isn't the ratio of the speeds the same as the inverse of the ratio of the indices of refraction? Isn't V1 over V2 the same thing as N2 over N1? If we have the values of N2 and N1, and we do, 1.47 and 1.52, lo and behold, we divide them, we get 0.98. So the ratio we'd say would be 0.98 to 1. Exactly what we did down here in blue, except a little bit quicker. Anybody have that thought? Yes? Did you do it that way? Good, good, excellent. Is it 0.97, not a 0.98? Okay, so it might have been a rounding thing there. We're not going to lose any sleep over that. Bottom line is, Tom, if you can divide those two numbers, 1.47, 1.52, and you get 0.97, then you're right? You're not going to make a mistake on that. Hey, I may have rounded wrong, or whoever gave me the answer may have rounded wrong, whatever. So not the end of the world. All right, the other two questions we had to go over were number 10 and 11. Number 10 involves critical angle. I'm just going to spend just a minute reviewing the whole idea of critical angle before we go over that question, okay? You guys remember we talked about total internal reflection, I believe on Friday it was. Okay, we got a boundary over to two media. We got a normal line drawn at 90 degrees to that boundary. We've got something with a high index, something with a low index of refraction here. Maybe it's air, maybe it's water, it doesn't matter. It's got a low index of refraction. And then we've got something with a high index of refraction over here. Maybe it's zircon, maybe it's diamond, maybe it's just glass, something with a higher index of refraction than whatever we start off with in the first medium. We got a ray of light that's coming down here. You know what? I always draw it on that side. I don't know why I always do that. Let's draw it on this side, just to change it up a little bit. Bless you. We're going to call this our angle of incidence. When that ray of light goes through that boundary into the second medium, what's going to happen to it? Speed up or slow down? It's going to slow down. We're going from a low to a high index of refraction. It's going to slow down. When it slows down, when V decreases, lambda will do what? The wavelength will do what? As n goes up, V goes down. Lambda will also go down. The wavelength will also decrease. What's going to happen to the angle? As n goes up, lambda goes down, V goes down, and theta goes down. So the angle is going to decrease as well. In other words, it's going to bend toward the normal line right here. We're going to say theta 2 is smaller than theta 1, right? N's going up, V's going down, lambda's going down, and theta's going down as well. Okay, if we increase that angle of incidence even further here, okay, we're going to increase our angle of refraction here, but the angle of refraction will always, no matter what, be smaller than the angle of incidence. As long as they're going from low to high index refraction, the angle of incidence will always be greater than the angle of refraction. All right. Can't get total internal reflection taking place there. But what if we do this? What if we go from a high index refraction to a low index refraction? We got our ray of light coming down like this. We got theta 1 labeled right there. N is going down. What's going to happen to V? What's going to happen to the speed? Increase or decrease? Increase. Okay, if speed increases, what's going to happen to theta? Theta going to go up or down? Theta 2 going to be bigger or smaller than theta 1? Just looking for a one-word answer, guys. Daniel, what do you think? Bigger or smaller? Like this? Okay. So if the speed is increasing, and it is increasing because we're going from a high to a low index refraction, if V is going up, theta is going down? Is that right? Who agrees? Okay, who disagrees? Okay, we got a few more people disagreeing than agreeing with you, Daniel. Okay, the disagreeing people are right, actually. If V goes up, then theta will also go up, right? It's V1 over V2, sine theta 1 over sine theta 2. Those are directly proportional to each other, right? Well, not quite, because there's a sine function in there, but not linear. But as one goes up, the other one goes up. So as V goes up, right, V1 goes to V2, a bigger number, then theta 1 is going to go to theta 2, a bigger number as well. So it's going to bend this way, right? It's going to bend this way. If I increase my angle of incidence to a great enough value, then we're going to get this light skipping along the boundary there. If I increase it even further, it's going to skip right off. What do we call that process when the light skips off and bounces off the boundary? Total internal reflection, right? What do we call this angle right here? This theta 1 value right there, at which total internal reflection begins to occur? Critical angle. The critical angle is theta 1. The angle of refraction at that point is what? We're going to set theta 2 in that case equal to 90 degrees. So whenever you're solving for the critical angle, and that's what you're doing in question 10 to 11, we're going to say Snell's law, sine theta 1 over sine theta 2 equals lambda 1 over lambda 2, V1 over V2 equals N2 over N1. But theta 2 will be 90 degrees. And we're going to rename theta 1 theta C. Sine 90 is what? Always. 90, what's sine 90? Right. So we're going to say sine theta C over sine 90. If you want, you can just drop the sine 90 right off of it because it's always 1. Sine theta C becomes N2 over N1, or theta 2 always becomes the inverse sine of N2 over N1. All right, so let's take a look at those two questions now. 10 to 11. The critical angle for zircon. What's the index of refraction of zircon from that table? 1.92? Now, it doesn't say what medium we're coming from, what medium we're going to. We have to assume, if it doesn't mention any other medium, that we're talking about air. Air is an index of refraction of 1.00. On that table, it actually says 1.0003, okay, but on our data sheet, it's 1.00. That's what we use. If you use 1.0003, you'll end up with a slightly different answer, but it'd be pretty close. Quantify the critical angle. So we're going to say sine theta C over sine 90, which is just 1, equals N2 over N1. Or theta C is equal to the inverse sine of N2 over N1. Which one's N2? Which one's N1? We don't know which way we're going here, do we? Are we going from air to zircon, or are we going from zircon to air? We're not told. Do we know? Yes, we do. How do we know? How do we know that it has to be one way and not the other? You can't get total internal reflection taking place when you're going from a low to a high index refraction. It's got to be high to low. So this is going to be N1, and this is going to be N2. The good news is if you mess up on that, as Maria just said, you're going to get an error on your calculator. So they'll tell you. Your calculator will tell you that you messed up on it if you do. N2 over N1, so it's going to be the inverse sine the inverse sine of N2, which is 1.00 over 1.92. Okay, what do you get in your calculator when you do that? 31.4 degrees. I think we found the other day the critical angle for glass to be somewhere in the range of 42 degrees. Okay, the critical angle for zircon, which is like cubic zirconium, right, the fake diamond, 31.4 degrees. We talked about the other day the idea that the smaller the critical angle, clearly the more chance we have of total internal reflection. Since diamond has such a high index of refraction, it has a really small critical angle. It allows total internal reflection to take place more, which means, of course, we're going to get more sparkling taking place within the diamond. Cubic zirconium is going to sparkle more than glass is because the critical angle for glass would be somewhere in the range of 42 degrees. You'll get more reflection taking place within zircon than you will within glass. Now, let's find the critical angle for diamond as well, just to compare those. Once again, it's going to be the inverse sine of N2 over N1. Diamond, well, diamond is 2.42. Air would be 1.00. Which way are we going? From air to diamond or diamond to air? We know this for sure. Devin, which way are we going? From air to diamond or diamond to air? Got to be diamond to air. Got to be high index to low index. If you're talking about just refraction, it doesn't have to be that. But if you're talking about total internal reflection, it's got to be high to low index refraction. So we're going to say this is N1 diamond, this is N2 air. So we're going to say theta C is equal to the inverse sine of N2 over N1, 1.00 over 2.42. And I think that works out to be something like 24, isn't it? 24.4 degrees, thank you. So 42 degrees for glass. You'll get some reflection taking place within glass. But zircon, you'll get a lot more because you don't have to have as big of an angle to exceed the critical angle. Anything above 31 will cause total internal reflection. Diamond, even more, because any angle above 24 is going to cause reflection to take place. Right?